start streaming. Let's look at the elbow of the Thormang robot. Then, as long as my coordinate system is in a fixed position relative to this link, it would allow us to calculate the forward kinematics. So I could put the coordinate system there or there. I can have x point this way or towards the front or up, and z can go anywhere it wants. So in theory we have a lot of choice there. Then with Hartenberg Convention, makes our life easier by constraining us. So it leads to a simplified setup. And in the DH convention, one way of thinking about it is that our transformation matrix is a 4x4 matrix, right? Now, just open those. This is where we ended up last time. So our transformation matrix shouldn't be Dij is equal not minus. It has a rotation matrix 3x3. It has a 3x1. And then on the bottom row, because we're dealing with homogeneous coordinates, we would have 0, 0, 0, 1. So for that 4x4 matrix, we know 4 numbers. So we need to calculate 16 unknowns. However, the last row we know is 0, 0, 0, 1. So that means we're left with 12 unknowns. So Dennevit-Hartenberg Convention comes up with a clever way so that we only need 4 numbers. To define the transformation matrix. So instead of 12, I only need to find 4 numbers. And it's pretty clever in the way that it defines that. So the first thing to realize is that the rotation matrix Forward kinematics cannot be opened. How come? Share. This is the link for forward kinematics, and right now I'm working on Hartenberg Convention. So that would be here. So the rotation matrix component, let me just copy that. This is a weird error. How come text decoder? Let me just run the forward kinematics. Maybe it doesn't work with Microsoft Edge. Maybe you have to use Google Chrome. And then I can download it, yes. So for me it works. But you have to use Google Chrome or Firefox. seem to work. Otherwise, we can also suffix. Where do I have a suffix? Okay, runtime, restart it. Okay, so our Hartenberg convention, let me just rerun the previous slides. Not this, but so this is what it looks like. Now the rotation matrix from R from I to J is a 3x3 matrix, but it is, because it's a rotation matrix, it only measures the rotation with respect to each axis. So that means I can actually define it completely by 3 Euler angles. Rotation along X, a rotation along Y, and a rotation along Z. X, Y, and then Z. Now for the Euler angles, it's important to realize that the order is important. So if I rotate z first, then y, then x, then I get a different result from rotation x, y, z. So we have to make sure that we rotate them in the right order. However, it means that 9 variables here can be defined by 3 values. So that means I really only have 6 unknowns. So let me see this one here. Did it go all the way to the end now? Yeah. Build deer content build deer doesn't make that one yet. It's not made yet, I don't think. Okay, so I'll have to fix that before you can watch it on GitHub. But this forward kinematics now, you should have access to it. Anyone on the link can view, and that will be the link. But I guess it doesn't work with Internet Explorer or Microsoft Edge. So then a big Hartenberg Convention only uses 4 numbers. So that means that's not magic, right? We cannot make up numbers, but we have to put in some constraints about the relative position where the coordinate systems are attached to the link. So this is possible through clever choice of the position of the coordinate frames to simplify the analysis. Otherwise, that wouldn't work, right? It would be just magic. And here, I don't actually need this part, I think. So the first assumption, or is that we align the coordinate systems with the axis of actuation of the joint. And the axis that we choose is the z-axis. The axis of orientation, axis of actuation of a revolute joint is the axis that we rotate around. The axis of actuation of a prismatic joint is the axis that we translate along. So if we're looking at the Thormang robot, here we only have revolute joints. But this constraint now means that the z-axis of this joint here, for example, this joint, would be pointing outside of the page or into the page. Because the joint rotates like this. So the axis of rotation has to be 90 degrees to the plane in which the joint rotates in, which means it'll be out of the paper or into the paper. This joint here, the shoulder joint, the axis of actuation would be here, it would be coming out of the paper or going into the paper. Here it's pointing to the right or to the left. Right. Here we're going out of the paper. Here the axis of actuation would be going up and down. And so that means for the coordinate systems, we now constrain them. The z-axis of that coordinate system for this joint has to be along this line here. The z-axis of the coordinate system for this joint is going in or out of the paper, and the z-axis for this joint is going up or down the paper. So then, the joint variable is also associated with axis x then. So joint variable theta I will rotate along z of coordinate frame I, and the prismatic joint, the joint variable di will translate along zi. So that's an assumption that allows us to place the coordinate systems, but it doesn't really constrain us very much. Doesn't actually allow us to simplify the number of variables that we need. However, this assumption sort of is not really detrimental, right? It sort of makes sense. If you didn't know about Hartenberg, you would probably align the coordinate system so that they coincide with the motors, right? That makes sense. So in this case, we do the same thing. We just formalize it and specify that we do that for all the joints. So then we make a further assumption. And that assumption is that we assume that x of I plus 1, so the x-axis of the next coordinate system and zi, the z-axis of the previous coordinate system, are perpendicular to each other. And this is called Hartenberg assumption 1. So how does that help us? If two vectors are perpendicular to each other, then the dot product of those two vectors must be, I think if I interpret them now as vectors, then I leave them as lowercase. So that means x xi minus 1 multiplied by z I dot is equal to 0. So that means that as far as the rotation is concerned, my relative, the x-axis of the previous join with respect to the x vector, that will give me xi will be r11, r12, r13 transposed dot, and then the vector for z in the current coordinate system would be 0, 0, 1. And that must be equal to 0. And because the rotation of x, if I write out the transformation matrix, I put it. Here I can write this as transformation matrix again in extended form. So that will be C, 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 C. R11, R12, R13, and now I call this variable O. One, 4. Okay. 0, 0, 0, 1, 0, 0, 0, 1. So this will be 2, 1, 2, 2, 2, 3, 2, 4, 3, 4, 3, 1, 3, 2, 3, 3. So here's our transformation matrix. Now, if I take that matrix and multiply it by the vector x, then vector x will be 1, 0, 0, 0, 1 in homogeneous coordinates. Right? So that means I get 1 times R11 plus 0, 0, 0, which gives me R11. And then I get R21 multiplied by 1 times R22, R23, O24, R31 multiplied by 1, so on and so forth. So I end up with this. If I multiply by the x vector, I will only get the first 3 numbers here, the first column of the rotation matrix, R11, R21, and R31. So that's our previous x vector multiplied with our rotation matrix then, right? Because we bring it into our coordinate system. So then if that's only R11, R12, and R13, all the other values are going to be 0. And our current z coordinate is 0, 0, 1. And then that has to be equal to 0. So from that, we can now figure out what happens. So for one thing, R31 must be equal to 0. If I look at the dot product, it's R11 times 0 plus R12 times 0 plus R13 times 1. So R13 must be equal to 0. No other choice there. Also, the rotation matrix from I minus 1 to I can be broken down as a rotation around x, angle theta, and the rotation x along alpha. And if I multiply that out, then I get the following matrix. cos theta sine negative sine theta multiplied by cos alpha and sine theta sine alpha then we have sine theta cos theta sine alpha cos alpha, yeah, negative cos theta sine alpha. Now R31, right, that's the one we already know, that must be 0. And then we have sine alpha and cos alpha. Okay, how come this is like that? Can conclude. So here and I guess I will use this opportunity to introduce you, see how it goes, introduce you to a nice little Python package called SymPy. It is actually pretty neat. So here I have a fairly complicated matrix multiplication. Of course, you could calculate it by hand to make sure that it's correct, and you should do that, but if the equation is more complex than that, it's easy to make a mistake. And there are symbolic math packages now that help you do that kind of processing that is going on. So here I only have the rotation matrix, so this line needs to go. Only 3 by 3 values. Right? So I haven't used SymPy in a while, but it is a very nice package. So let's try and see and verify the multiplication that we have here. So we have SymPy and tutorial. So this is a SymPy package that I was talking about. Now let me remind myself how we define variables. So that would be and theta right. How come my SymPy is gone now? Oops. Sorry, from the wrong package, wrong file. So here, so theta and alpha are equal to symbols. And T and A oops. Can define that we want to use Unicode printing, then it makes it look a little bit nicer. Go away. define how to define the rotation matrix. Okay. Rx theta and Rx alpha. I think it goes like this. Shape inserting. Rxt is equal to matrix. And then I need, so if we rotate around angle x, axis x, then did I copy that here? That will be this rotation matrix here. So it would be 1, 0, 0, 0 cos. Then with Hartenberg. Actually, I think that's a mistake there. It should be RZ. Let me try. So what did we have? Sine t, no, 1, 0, 0, zero cos t, negative sine t, and 0 sine t cos t. and I just leave the namespace out because otherwise it's going to, I'm going to get confused if I use math cosine or SymPy cosine. So where do I print the matrix? Display HTML RXT. I would print it nicely if I evaluate it. Print. Alright, so this will be RXT, and then we set RXA alpha, so that will be A, and R is equal to RXT dot RXA. Yeah. So that should be RZT. Negative SymPy dot sine t 0 SymPy dot sine t pi cos t 0 0 0 0. Simplify. 1 0 0 0. Wait. How come we have I think it's not calculating the dot product. Matrix multiply. Oh, dots. Okay. Yes, so here we can now get our matrix, and this should be not X, this should be Z here. See if there's a pretty print. Init printing. Integral string. Pprint. Okay. Let me try that. So as you can see, this is actually pretty neat, right? We can now do mathematical calculations using, and I wonder if I can change this to, yeah, then that would look even cooler. Where are the Greek letters? Greek letters, theta. alpha. Yep. So now we have cos theta, negative sine theta, cos alpha, sine theta. I don't know why it swapped them there, but okay. Sine theta, cos alpha, cos theta, negative sine alpha, cos theta, 0, 0, 0. So the first part is correct. I think I made a mistake there. Yes, that should be 0, 0, 1. Yep. And now you can see this is actually, it's not a proof, it's not a mathematical proof that it's correct, but it's exactly this matrix here. So SymPy is, if you ever have to solve, it can do integrals and derivatives, many other interesting functions. If you ever have to solve them, for example, third order polynomial or something like that, it's very easy to make a small mistake and then end up with the wrong answer. It pays off to double check your work using a package like SymPy, and there's also several other ones, but it's pretty neat that we can do it that way. Let me see if there's a HTML, Unicode, pretty printer, LaTeX. MathML. Okay, let me try this one. Oh, no, this doesn't look so nice. Okay, so better stick with the ASCII printing. So now let's continue with the Hartenberg Convention. So the first assumption is that z, x minus 1 and z intersect. The second assumption is stronger. It assumes that x I minus 1 and z I actually intersect. This is then with Hartenberg Convention, assumption 2. So that means that the displacement from the coordinate system, from the origin of the coordinate system from 0 to r minus 1, can be expressed as a displacement along z and xi. Technically a linear combination, yes. So what does that give us? Now the should be I minus 1. So O from I minus 1 to I is equal to left, right, again array, so the displacement from the origin from I minus 1 to I minus 1 is 0, right? There is no displacement, so that will be 0, 0, 0. Then plus a translation now by d along z, plus, and now we have, we rotate by theta, oof. What's wrong there? Oh. So displacement from I minus 1 to I, the origin, displacement of the origin for is going to be a linear combination of zi minus 1 and xi. And then here we have, this is a mistake. That means OI minus 1 from I minus 1 to I is 0. There's no displacement here, plus the displacement along z, plus, and then we rotate to align with x. That rotation depends on the joint coordinate theta, and I want to get rid of the brackets here. And that means then I can multiply that out, right? And this should be plus a multiplied by that, so that means OI minus 1 to I is equal to that will be I cos theta A sine theta and D. Right? That's just multiplying out this equation here. So now let's have a look at or what the Denavit-Hartenberg assumptions 1 and 2 give us means that from the previous joint to the next joint I can get there by translating along z. Then x has to be 90 degrees to z, and they have to intersect the next x. So this is joint 3, this is joint 4, x-axis, they have to intercept. So I need to go joint 3 along z until I hit that intersection point. Then I follow along the new x direction. Now that's going to be influenced, the new x is going to be influenced by my joint variable. So that's why I have a cosine and a sine there. the relative orientation of those two variables. Actually, with a prismatic joint, then it may be the constant angle between the two to align the x coordinates from the previous to the next frame. Then let's use SymPy for that again. So transformation matrix A for joint I would be equal to rotation of z by theta followed by translation along along z by d followed by translation along x by a, followed by rotation along along x by alpha. So to get from the previous coordinate system to the current one, is rotate along z by theta, translate along z by d, translate along the x by a, and then rotate along x by angle alpha. So that's where our four values come from, our four numbers, right? Theta, d, a, and alpha are the four numbers. Theta, d, a, and alpha. Good. So now let's see what that rotation matrix actually looks like. And let's have some more fun with SymPy. So the rotation should be z. I now just need to define all the transformation matrices. So RZT is rotation along z by angle theta. I also have some more variables. So now I need to define the translation along z by distance d. And I need to have these matrices as 4x4 matrices in homogeneous coordinates. So I need to add a row of zeros and the last row, 0, 0, 1. Then here the same, 1, 0, 0, 0, 0, 0, and 0, 0, 0, 1. So displacement along z is easy, right? That's 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. And this here should be d. Sorry, not this one. This one here, we translate along d for the z-axis. Then we translate along x by a. So that would be here, that's added to a, and here that should be dd. Oh, no, not this one. This should be dd, and this should be t xa. We have 1 AA, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And then we have rotate along, rotate by theta around axis z, translate by z by distance d, translate around x by distance a, and rotate around x by angle alpha. And then this is what we get. So cos theta, negative sine theta, cos alpha, sine theta, a multiplied by cos theta, sine theta, cos alpha, cos theta, negative sine alpha, cos theta, and a multiplied by sine theta, and then 0 sine alpha, cosine alpha d, and then 0, 0, 0, 1. So this is the correct transformation matrix now, the one that we can derive from Denevit Hartenberg assumption 1 and 2. All our transformation matrices now are going to have this form. Now the link parameters they actually have common names. So theta is called the joint angle. D is called the link offset. A is called the link length. And alpha is called the link twist. Now, theta and d are our joint variables that we control. If it's a revolute joint, we control theta. If it's a prismatic joint, we can change d. We can control d. So let's have a look at what these variables actually mean. Start with theta. So joint angle theta, oh, I have to add a space there, joint angle theta. Let me use the Greek letters. Is the angle between the previous x axis and the next x axis. And so x from I minus 1 to xi. The link offset d is the distance from the origin of OI minus 1 to the intersection point between x, between z, I minus 1, and xi, measured along z I minus 1. Next we have A, the link length A is the distance between z I minus 1 and zi measured along xi. And last we have the link twist alpha let's see so where did I put the NumPy? Here. No, I need alpha. So alpha is the angle between z I minus 1 and zi measured in the plane normal to xi. So given the Hartenberg Convention, the variables that we define, they sort of make are also of intuitive sense, like these values are sort of something that you can relate to when you're dealing with a real robot. Now for humanoid robots, often we actually break, or I usually, yes, I sometimes break the Hartenberg conventions because we'll see when we go through the example of the Thorman kinematics. Sometimes you can cheat a little bit and you get the coordinate systems in slightly nicer positions by not following the Hartenberg convention. However, you can actually prove that the Hartenberg convention is able to describe any robot system. So it is not a convention that restricts you to only certain kinds of robot systems. For any robot, we can align the coordinate systems in such a way that we can follow the convention. That is true for humanoid robots as well. But it is not the law. So sometimes you can break the convention and nothing bad will happen, and you get a result that's maybe slightly more pleasing or slightly easier to understand when you reason around it. The big problem with robotics and kinematics with humanoid robots is that it's quite difficult to debug in a sense, because all you get are floating point numbers. And then if one of the numbers is wrong, it's not so easy to figure out why it's actually wrong or to even recognize that it's wrong. If you do C programming or Java or Python and you deal with arrays and you make a mistake, then you get a array index exception, for example. You get an error saying that, oh, you're accessing array at location 20, but your array only has 19 elements. Then your program will crash. Then you can investigate what the problem is, and you can sort of figure out where the problem occurs. But in kinematics, you never get a crash because they're all just floating point numbers, so the computation is just going to move along. You just get the wrong result. And it's not so easy to then figure out where the error actually comes from. So that's the that's one of the problems with robotics. You have to be quite careful in the way that you're dealing with those numbers, that you set up your coordinate systems. And that's why I think Matplotlib is a really useful tool, because you can draw what the coordinate systems look like, whether that makes sense or not. You can check on your robot to read the angle between the joints and then see if your robot moves in the same way. And then it's easy to track down the problem, much easier than just looking at 16 floating point numbers that are on the screen. So now let's have a look and see how we're assigning frames for kinematics using the Hartenberg Convention. So we start with the inertial frame. And then iterate to 1 up to n, or from 1 up to n. So axis, the z-axis can be assigned arbitrarily since I can rotate by alpha I and theta I. theta I, theta I. So we pick intuitive directions for Z0 Z m minus 1. And like I said, that means the convention is that axis zi minus 1 is the axis of actuation for joint I. Let me just double check that I didn't mistake there. Variable joint variable theta I will rotate along the axis zi minus 1. Yeah, so it's the previous z. Not the next one. Yes. Because the index for joints and links is off by 1, so joint I is independent of link I minus 0 to I minus 1. Or joint I will only impact the links I to N. Comma. We can then set up the world frame, inertial frame, the world coordinate system. Frame 0, that all means the same thing. The origin of inertial frame must lie somewhere. Since it's an origin, it must include Z0, so it must lie somewhere along Z0. But we still have a choice for X and Y, so set up axis x, x0 and y0, y0 in such a way that it makes sense to you. That it makes sense and is a right-handed coordinate system. That's really the only constraint. It must be a right-handed coordinate system. Okay, good. So now I want to have a little break for 30 minutes. That way I can get up a little bit and walk around, and so we will have a break until 20:30. Okay, and then I can also have dinner.